Thanks, Richard. So yeah, we co-teach this module on computational mathematics. So we're going to be co-presenting like a well-oiled machine, but Richard is in charge of the slides. So timing is all down to him. And in fact, having said hello, I'll let him go through the contents of the talk.
Great. Yeah, so, well, we'll talk about three aspects of this particular module that we're both involved with, computational maths. We'll talk about its history, what it is, why we've taken this approach to computational maths. And then we'll talk about how we have been teaching it up until last year. And then we'll talk about, well, our plans for teaching it starting next week, really. So hopefully some aspect of that will be of interest. So let's start with what it is and why. And I think that's Rob.
Yeah, so computational mathematics for us, we take a very broad view of this. It's really any time you do mathematics using a computer. So in particular, it isn't just numerical analysis and learning to code those sort of techniques. I sort of think of that as when you use a computer, when you already know exactly what you want to do, but you lack the time to do it. In a sense, that is numerical analysis. But we also want to really push an idea of using a computer to do investigative mathematics. So the idea of, you know, here's a mathematical problem that is extremely hard and an undergraduate wouldn't be expected to solve or possibly even to address the problem. But you can use a computer to either get some evidence, to explore the problem, and to encourage our students to do investigation. So that's really the aim of the module. We want to do this by introducing some really core and fundamental programming techniques, which we can test, and then basically encourage creative thinking and open-ended problem solving. So in terms of the logistics of the module, it's a level 2 mathematics module, which is compulsory for all our maths students and optional for lots of joint honours students. So it's a big class of 320 students. We're using Python as the language of choice, essentially because it's free and open source. And I think that is a huge benefit to have made that decision. Now we're going to be teaching it all remotely. We're using the Anaconda distribution as a good one for a nice graphical interface. And we do have, this is a compulsory sort of first course in Python and computational maths, but we have courses that follow on from this in both pure and applied. So we have logic with computation, numerical analysis with computation, discrete maths with computation. And I think a lot of the ideas that we're talking about here are also being used in statistics in Leeds, but we will only be talking about computational mathematics here. So I think finally, just the aims of this course, I think are illustrated in the next slide, which Richard can talk about.
Yeah, thanks. So to sort of flesh out some of those ideas that Rob was mentioning, we've got a couple of examples that feature probably about a quarter to a third of the way through the module, I think. So illustrating both the sort of conventional programming approach in the case of this question. So here's a question which says, here's a familiar piece of mathematics, Euclid's algorithm, write some code to enact that, as it were. So that's something you can, you know, the students are either going to do it right or wrong. And one benefit of that, of course, is that their answer can then be checked largely automatically, because either their algorithm does the right thing or it doesn't. You might want a human eye to eyeball it as well, just to make sure they haven't, you know, imported the Python's GCD function and applied it. So this is a sort of a pretty straightforward question using familiar mathematics and sort of basic coding questions. And then a follow-on question is, as Rob was saying, more open-ended and investigatory. So here are a couple of results, theorems about Euclid's algorithm and its running time, its computational complexity, essentially. So the number of steps that Euclid's algorithm takes at most or on average. And I think it's very unlikely that students would be able to prove these results. And certainly that the intention is not that they should try, but rather they can usefully investigate these following their own nose. So there are various things they could do, there are different approaches they could take, And there isn't so clearly a right or wrong answer, but there are definitely better or worse answers. And of course, this is a reasonably open-ended, but there's a possibility of making it even more open-ended by not presenting them with the theorems and just asking them something more general, like how long does it take Euclid's algorithm to run? So that example there is about Euclid's algorithm, and we found sort of similar little seams of material across pure and applied mathematics where it's possible to ask questions in both of these two ways, so quite specific questions, but then also broader investigatory questions. I think it's fair to say that elementary number theory is a particularly rich seam, but as I say, there are plenty of other areas that we investigate and ask the students to do as well. Okay, I think the next slide is about how we've been teaching it, and that's for Rob.
Yeah, that's right. So I'll just talk about how this module usually runs, and then I guess flag up the sort of things that we're going to want to try to keep or change in our plans for this year, and hopefully then Richard can give us some practical advice on how we plan to do this. So in normal times, this lecture runs by having one lecture a week, and we stand in front of the class of 320 students, and roughly half the time we deliver some mathematical content, tell them the mathematical background or the mathematical foundations to what we're trying to do. And then we show them the coding, and we do live coding in front of them as they watch us do this. And clearly, this won't be possible this time, or it won't be desirable to run these lectures in exactly the same way. The students do their own coding in workshops. So after the lecture, they'll go to one of a set of workshops that run in a cluster room in groups of around 50, staffed by demonstrators who are there to help. And I guess there are really three things that we want students to be able to do in these workshops. And one is simply sit and work on their own if they want to on the problems that we set them, work their way through example sheets. The second is chat to their friends and sort of ask their neighbor or in small groups to work together on a particular problem. And finally, to get help from the demonstrators who wander around the class answering questions, looking over shoulders, and that sort of thing. So whilst teaching us remotely, we want to be able to keep all of those three elements. How do we assess it at the moment? So we assess it, we want to test their core competency in coding, whether they've managed to grasp the fundamental techniques. So we set weekly practice sheets, and some of these are assessed for credit and some of them are just for formative feedback. And as Richard said, some of these are good for automatic marking, and there are various tools out there to do this, like Gradescope. Now, in fact, when we started trying to do automatic marking, Gradescope wasn't available at Leeds University, so we wrote our own essentially automatic marking software, adapting some work that had been done in electrical engineering in Leeds, and there's a link at the bottom there, a reference to our colleagues who started this program. And I think the benefit of our homemade version is that it's really easy to combine the automatic marking, which generates marks and generates automatic feedback, whether the student has got it right or wrong or made a common mistake, with then a pro forma document that we can easily annotate with the comments that we want to make about the more open-ended questions. And then the dissemination by email of these feedback sheets is really easy. Possibly Gradescope will do all of that, but as I say, we had to do this from scratch. We also assess them on this open-ended investigations, and we set them as sort of a project to work on. And again, they can be from any bit of mathematics, and they tend to be a mix of trying to test some core competencies that we can mark very easily and automatically, and open-ended things. So for example, the Goldbach conjecture says that every even number bigger than 2 can be written as the sum of 2 primes. Investigate. And so we would expect the students to write some functions that are very explicit, that we can test that they work automatically, and then just work on giving us some evidence for the truth of this conjecture. And the last bit of the assessment that we normally do is a pen and paper test. So we normally just set this in a lecture theatre. We, I guess, want to test two things here. This is a chance to make sure the students can do something definitely individually. They're definitely working on their own. And they're also working without a computer normally, doing this on pen and paper. So for that, when we're working remotely now, we definitely want to keep the first of those elements, and we certainly can't keep the second of those elements. Back to Richard.
Thanks. So this is more or less our last slide. And this is talking about how we're going to adapt what Rob's just been talking about to online delivery. So we're planning 100% online delivery for this module, no face-to-face teaching at all, we expect. So the first thing we've done is address the lecture aspect of it. So the lecture, as Rob said, we covered both the mathematical and the computational side of things. So we've separated those two out. That's the first part of the plan. So the mathematical content will be delivered by pre-recorded videos, and then the computational content will be delivered through online live sessions. So we will be online with the whole class of 320, and we're calling those sessions code-along sessions. The idea being that, unlike in the lecture theatre, all students will be sat in front of a computer, and they can have their Python editor open alongside us, alongside the screen where we're speaking. So that allows us to do a few things that we couldn't do before, such as share code directly in the session through the chat function, for example. So we're expecting to disseminate bits of code, to talk about them, maybe to give them some time to think about why, or perhaps to discuss why some particular bit of code is broken, or these sorts of activities. Good. So that's what we're doing to the lecture, as it were. We're pulling it into two. Then the other big problem was the workshops. So these are going to be in similar group sizes as previously, groups of about 50. And rather than in computer clusters, we're going to use Blackboard Collaborate Ultra. So Rob and some colleagues tested out a few platforms to see which was the likely to work best. I think they tried Collaborate Ultra, Teams, and Zoom. I didn't participate in this because I was being an admissions tutor at the time, which is a whole other saga. And they decided that Collaborate Ultra was going to be the best of the three, I think, for two main reasons, as I understand it. Rob can jump in if I miss something. So the two main things we wanted is, firstly, to be able to share snippets of code using the chat function. Now, some of those, I think Zoom, for example, breaks the formatting of Python code if you share it in the chat function. That seems to be the problem, because Python code, white space is a really important part of it. The tabbing has to be, the indentation has to be correct. So if that gets broken, then the code doesn't run. So Collaborate Ultra, the chat preserves that side of things, which is important. So the other aspect, which we think is going to be really important, is the use of breakout rooms. And we're expecting to use breakout rooms, I think, in two different ways, really, in these sessions. One is sort of preordained problems that we put in the sheets specifically for discussion by students in breakout rooms. So in groups of 4 or something, give them something to talk about, interact. And the second way is more organic. And this is to try to get the same sort of availability of demonstrators that we were getting by people just putting their hands up in a computer cluster. So in a computer cluster, someone put their hand up and say, I'm really struggling with question 2B. So they can do the same thing on Collaborate. And what we're expecting then is that the demonstrator will then start a breakout room and tell the whole class, right, someone's struggling with question 2B, so I'm going to talk about that. If you're interested in that, then jump into this breakout room. And this has, at least on the face of it, this seems to have a real advantage over doing it in the computer clusters, where either you're having to answer the same question multiple times to lots of individuals, alternatively, you're telling the whole class, but maybe half of them aren't interested, so you're sort of distracting them. So this has the opportunity to really direct that particular conversation to exactly the students who need it. So moving down this slide, then the two next pieces are in small font. That's illustrating those are unchanged. So the sort of standard sheets and the mini projects we're expecting to be more or less unchanged. But of course, the timed test is, or the test is going to be different. So that's going to be online, and so it's not going to be pen and paper. So they're going to have a Python editor in front of them, and of course, they're also going to have Google in front of them. So we have to adapt the test correspondingly. Now, this is one aspect we haven't thought through fully because it's not going to happen for a couple of months. But the sort of thing we have in mind is a question along the lines of we give them something to investigate and ask them something about it. So, for example, is an example of Rob's. Here's a bit of code which demonstrates, which defines a 1,000 by 1,000 matrix, and we can ask them in this online test to tell us the determinant of the 2 by 2 matrix which is in the middle of it, or something like that. This has the advantage that you can't really get very far Googling. You'll spend all your time Googling, not thinking about it. And it also allows for sort of randomizing so that to prevent students from colluding with each other. So that's an overview of what we're planning to do. I think we're coming up to our time limit. So thank you very much.
So thank you very much to Rob and Richard for that really quite helpful and interesting talk. So I'm Eleanor Jones. I chair the RSS Special Interest Group in Teaching Statistics. So I'm going to be looking at the Q&A today and posing your questions to the speakers. So please, if you do have any questions, please pop them in the Q&A. So we've got a couple of questions for you already. So a really interesting question, first of all, from Simon Harden. How do students feel about automated rather than human feedback? So is that something that you've thought about at all?
Do you want to take that, Rob?
Sure. Well, I'll start. I think okay. So with our system, I mean, the bits that are automated, what we do is write our own human sentences in it to start with. Okay, so you know, if the students have been asked to write a particular function and they've got it right, then you know we can write whatever we like in our automatically generated thing. You know, well done, that works well. Or if they've got it wrong, we've pre-populated our automatic software to say not just incorrect, but you know, this seems to be wrong for this reason. Have you tried doing the other? And then after, as we said, after we've generated all of the automatic bits that we can, we then go through and just annotate with extra comments where we would if we were doing normal, I guess, pen and paper sort of responses. So I think we never just leave it as purely automated. It sounds like it's coming from the computer sort of responses.
Okay. Thank you very much for that. So we've got some more questions coming in now. So about collusion, so you were talking about how you were trying to get around or sort of prevent students from colluding. So one question here is, students produce code so they can collude by sharing code rather than numerical answers. Is randomization still going to be effective against such collusion? That's an interesting question.
It is an interesting question, and I think it's fair to say that, you know, the fight against collusion is ongoing. We don't claim to have, you know, completely solved all the problems. So I think that question is particularly directed towards the test, by the sound of it. I think the test is where we're going to use randomization, and I think we haven't completely thought through exactly what's going to go in the tests. We're certainly conscious that of this sort of issue. I mean, if students write a program which produces that determinant, regardless of the starting matrix, then there's no protection against collusion. That's clear. So we're aware of that problem. There's some randomization in which questions arise. That's a possibility. I think in the coursework side of things, the open-ended aspect of it really is some protection against collusion, because it's not easy to tell whether, two people have colluded to produce a particular function to do this. But once you've said, you know, investigate this more general problem, much easier to spot where things look suspiciously similar, I would say.
Okay, thank you very much. I think we're out of time for questions. There are some more questions in the chat if you'd like to answer those, but I'll hand it back to Jocelyn now.